Welcome to Hence the Future podcast. I'm Mattimore Cronin, and today we're discussing AlphaFold and the current state of AI. That means we'll get into the recent breakthrough that just occurred, which is that Google's DeepMind has finally solved the 50-year-old protein folding problem with their new program, AlphaFold 2. We'll also look at the implications that this breakthrough is likely to have on the future of bioengineering, and we'll take a look at the current state of artificial intelligence to assess how close we are on the path to artificial general intelligence. First, I want to start with a quote from Andre Lupus, who's an evolutionary biologist at the Max Planck Institute. He's also one of the people that ran the CASP contest to determine which is the best protein folding prediction algorithm. And here's what he says about the impact of this recent breakthrough. Quote, "This will change medicine. It will change research. It will change bioengineering. It will change everything." So that's pretty amazing. And to understand why he believes AlphaFold 2 will change everything, we need to first understand what the protein folding problem is and why it's so crucial for biological systems. So what is the protein folding problem? Well, first let's talk about what are proteins. Proteins are the building blocks of any life form. So whether you're a plant, an animal, a human being, you have these proteins in your cells that are the doers of the cell. So anytime you look under a microscope and you see something interesting happening, something being carried from one cell to another, or some sort of work being done, proteins are playing a key role there. And we know that there's over 200 million of these proteins, but we've only actually been able to find out the shape of a select few of them. And the reason is that it's really hard with our current methods to find out what the structure of a protein is. We have to use a technique called X-ray crystallography, which takes up to a year and over $120,000 just to find out the structure of a single protein. So why is it important to know the structure of a protein? Well, depending on the string of amino acids, a protein will fold in a certain way. And depending on how it folds, that determines its actual function, what it actually does in the cell and in the organism. So one of the best ways to think about this is as, imagine a protein as being like a string of beads, and each bead is an amino acid. So you have this sequence of beads, and depending on what the sequence is, it will fold in a certain way. It's sort of similar to DNA, how DNA is the double helix and it's made up of G, C, A, T, and depending on that sequence of those four letters, you can determine what someone's DNA genetic code is. It's very similar for proteins, except it's even more complicated because unlike where there are only 4 possibilities for DNA, there are 20 possible amino acids. So the possible combinations is astronomically high. I saw one estimate that said that there are 10 to the power of 143 possible ways that a protein may fold. So scientists have been trying to solve this problem for 50 years. That's why it's often called the 50-year protein folding problem. And that's because early on, scientists realized that if you could input the sequence of amino acids and then use computers and machine learning to output what the protein is likely to look like as a physical structure, that would be a tremendous breakthrough. So people have been working on it for 50 years, and since 1994, they've held an annual CASP competition. Here's how the competition works. Each team is given 100 sequences of amino acids for 100 unique proteins, and then each team does their best using their machine learning techniques to output a 3D model for each of those proteins. And then each team is given a score from 0 to 100 for how closely their 3D model matches the actual structure of the 100 proteins. And the teams don't know which proteins they're working with in advance. So it really is a black box where there's no visibility beforehand. It is a pure test of how well these systems can predict the structure of a protein. And this year they even had one of the proteins was a protein in COVID-19. So you can already see this is hugely potentially impactful for any sort of new virus and creating any sort of treatment. And what is really incredible is that Up until this year's competition, no other team had gotten close to achieving the threshold of 90% or higher, which scientists consider that to having solved the problem entirely, because at that point you have a close enough model that you can actually make leaps and bounds in how effective your treatments are. This year, for the first time ever, AlphaFold 2 from Google DeepMind achieved a score higher than 90. So now the protein folding problem that people have been working on for 50 years has been solved. And when you look at the results of the contest, it's not even close. AlphaFold 2 is just in another league ahead of the other contestants. So I'll show this chart in the video pod on YouTube, and you can see AlphaFold 2 is just blowing the other contestants out of the water with how accurate it is. And this is a breakthrough in the purest sense of the word. This is a new paradigm for biology, for health, for medicine, for environmental science, and the possibilities and the possible applications are tremendous. So let's talk about some of the possible applications of this breakthrough. First of all, most importantly, this allows us to understand biological systems to a far greater extent than we have in the past. So oftentimes in science, it feels like we already know a lot. Like, especially if you're sitting in science class in school, it feels like we've figured everything out and we're just learning and memorizing what the facts are. That is so far from the truth. The reality is that we only have a small fraction of the potential knowledge of biological systems. So I said earlier that there are over 500 million types of proteins that we know about, but there's only a handful that we've actually modeled the structures of. And the structure matters so much because that's what actually determines the function of the protein. So if we can actually map out all 500 million proteins, know what all of their structures are, that will allow us to understand biology so much more deeply than people in previous generations. So it really is a leap ahead in our understanding of biology. And it also is huge for medicine because think about, for instance, the coronavirus. This is a new virus that didn't exist in the past. And there are always new viruses being created. Current viruses will mutate. So now, anytime a new virus emerges in the world, we will be able to analyze the amino acid sequence, create a 3D model of that virus, and then see its weak points or see ways that we might be able to cure the virus or stop it spreading or possibly even reverse the damage that's already been done. For instance, we already know that Alzheimer's disease is a protein misfolding problem. So by understanding how the proteins misfold, we can come up with remedies and we could cure Alzheimer's. We could also cure totally new types of diseases, old diseases, and many diseases essentially come down to a protein misfolding problem. So the entire health space, drug treatment, drug discovery, other types of treatment, all of these have just leapt ahead as far as progress. It's also huge for the environment. You can use bioengineering to combat climate change. And one way is by breaking down plastics. So normally it takes millions of years for plastics to actually re-enter the earth and break down from their components so that they can be recycled and used by the earth. We may be able to bioengineer new types of proteins that can break down plastic waste much more quickly. We can also use bioengineering to remove carbon from the atmosphere. So decarbonization is potentially going to be hugely improved by this recent discovery from AlphaFold. And beyond that, there's also the general artificial intelligence implications of this discovery. Because let's not forget, AlphaFold was not created in a vacuum. It is in fact one milestone along the journey that Google's DeepMind has had on the path to artificial superintelligence. So let's take a look now at the current state of AI and assess how close we are or how far we are from achieving human-level intelligence in machines. Let's take a look at the previous milestones that DeepMind has achieved up until now so we can get a sense for where we've come from and where we're going. In 2013, DeepMind beat almost every Atari game, so games like Pac-Man and Space Invaders, using a technique known as deep reinforcement learning. So essentially, this machine would just play itself over and over and over again at Pac-Man or Space Invaders or any of these other games until it completely mastered the game and could beat any human score. from 2015 to 2016, that was when AlphaGo beat the world's top Go players. And this came already after IBM's Deep Blue had beaten Garry Kasparov, the world's top chess player. And Go is a much more complex game than chess. There are far more potential positions that the board can be in at any given time. And it's a game that requires more intuition than chess. So it would be much harder to do raw calculations in a top-down approach for a game like Go than you could with chess, for instance. In 2018, AlphaZero was a similar system to AlphaGo, but it was much more generalized. So whereas AlphaGo was built specifically to play and master the game of Go, AlphaZero is made to master any game. So it doesn't matter if you're playing Go or chess or any other game, the system will essentially learn how to master any game that has a value of how well you're doing in the game in order to create reinforcement. 2019, there's AlphaStar, so that's the next step beyond AlphaZero, where the system would essentially master StarCraft. So I don't know if you've ever played StarCraft. I used to play it a lot as a kid, and it's a much more realistic game than Go or chess or Atari games. You start to resemble the real world in a game like StarCraft. You've got multiple different teams, composed of computers, but also of other human players. You've got resources you have to mine. You build different structures. You go to combat. You need to understand the 3D environment and change your moves depending on how that environment is changing. So it's a much more multifaceted game than anything in the past. And in 2019, AlphaStar beat the top StarCraft players in the world. Now that brings us to 2020 with AlphaFold. Now, at last, we are no longer just in the world of video games. We've actually moved to the real world, to real biological physical structures. And this is incredibly huge. It means that we are moving out of this sort of sandbox environment and into a more real world environment where we could actually make real impactful changes for people's lives and for biological systems all throughout Earth and potentially throughout the cosmos. There's no way to know exactly how far we are from achieving human-level general intelligence in machines until it happens, but let's take a look at some of the major players and where they are to give us a lay of the land. So we already talked about Google's DeepMind. They've been making tremendous progress. There's also OpenAI, which was founded by Elon Musk, Sam Altman, and others. And this is probably the most advanced speech transformation AI in existence. So we did a whole episode on it on the podcast. So if you're interested on this topic, you can listen to the episode on GPT-3. But I'll explain it here briefly. GPT-3 trained on tons and tons of data in the form of books. So imagine feeding an AI learning system with all of the Encyclopedia Britannica, all of this other high quality, highly curated information, and the whole algorithm is made to predict what the next text will be. So if I start to write an essay on quantum mechanics, it will finish my essay and it will actually come up with really insightful sentences and phrases and paragraphs that is better than what most human copywriters would come up with, simply because it's so good at predicting what the next bit of knowledge should be in that essay. So I saw one example on Medium where he asked the system to come up with a description of strawberries for his daughter, and it came up with a super concise, clear, simple, easy to understand description of strawberries. And then he gave a different prompt where he said, hey, my boss asked me to come up with a scientific explanation of strawberries. Here's what I said. And then by giving it that prompt, it came up with a more scientific description of strawberries that sounded like it could be in any sort of scientific research paper. So the incredible thing about GPT-3 is that you basically come up with what you want the end result to be, and then you just work backwards to give a prompt that will lead to that result. And you can really work with the machine to a great degree, where you can change your prompt in subtle ways by using different adjectives for what type of response you want. Like, do you want a friendly response, a scientific response, an easy to understand response? And then the system will give you that better text based on what you're looking for. So I would say GPT-3 has incredible potential, and it hasn't even really scratched the surface because it's really in a closed beta and they haven't allowed access to very many people. I think when you compare like DeepMind and OpenAI, I could see either one of them being the company to create true AGI in the future. And then finally, we shouldn't forget about China. China has had a recent surge in AI. They've been investing in it heavily. And part of why China has had so much success with AI in recent years is that they have much more data than companies in America have, and much more vertically integrated data. So whereas in the US, there's all of these different systems that you can use for payment, like Square or Cash App or Apple Pay or Google Pay or whatever else, in China, everyone uses WePay pretty much. And for instance, WePay has 900 million users, whereas Apple Pay only has 22 million users. So when you just look at how much data they're working with, their ability to train systems far exceeds our ability here in the US. However, when you look at what the consensus is that China has not yet surpassed the US in AI capabilities, but it has already surpassed the European Union. Now let's get into the future scenarios. Let's talk about the worst case scenario.
Worst case scenario.
The worst case scenario is what Elon Musk fears will happen with Google's DeepMind. And he has said that to him, DeepMind is a top concern when it comes to artificial intelligence. And the reason is that Google's DeepMind has admin access to Google's servers, which means that if there were a runaway AI scenario, it could do a lot of damage by having access to Google's servers and the entire Google system. It could access financial transactions, search transactions, it could modify results. So it is kind of the perfect potential storm if you were to think about a runaway AI scenario. A runaway Google AI scenario is probably about one of the most damaging potential outcomes we could have. So that is definitely a big concern. It's also a concern that these algorithms we've been talking about function as black boxes. So you put in some set of inputs, you get some set of outputs, but you don't really have a way of knowing why the inputs led to a certain output. So this is a little bit worrying because it leads to a potential future where we don't know why the machine is doing what it's doing, and we're not even really smart enough to be able to alter it in a way that would be more beneficial for humanity. And we're kind of taking the back seat. So if we don't do this right, if we don't develop AI in a safe and intelligent way, then we may only get one shot at it. So it's not like we can redo it. I mean, Elon has this other quote where he says, you know, people always say, hey, it's not like we have robots running around in the street. Why are you so worried? And his response is, well, once robots are running around in the streets, it's too late. The whole point is that we want to prevent the scenario where we've got robots running around willy-nilly in the streets. So we have to be very careful and diligent about how we develop AI. And the other concern in the worst case is if we don't move fast enough, if we're too concerned and we move too slowly, it's quite possible that China could surpass the US in artificial intelligence capabilities. And AI is one of those areas where if you have total supremacy in AI, it almost doesn't matter what else you have. Like, oh, you have a good Navy or Air Force or whatever. It just doesn't really matter as much. If you have better intelligence capabilities, it trumps everything else. You know, like think of the fact that, yeah, gorillas are a lot stronger than us, but our intelligence dwarfs the ability for gorillas to put up any sort of a fight against humanity. So just to conclude the worst case, I would say that we both need to make progress quickly so that we maintain our lead in the AI space. And we also need to be as safe and diligent as possible when it comes to developing AI that is truly beneficial. Now let's talk about the best case scenario.
Best case scenario.
The best case scenario is that by understanding protein folding, we will be able to cure every disease, even brand new diseases. We'll be able to reverse aging, so you can literally turn back the clock on your cells and only have to worry about getting hit by a bus. You no longer have to worry about contracting some disease and having a slow, brutal end. We could also solve climate change, which would be tremendous. We could bioengineer proteins to potentially terraform Mars or the moon or other planets. There are virtually endless possibilities once we understand biological systems to as great of a degree as we could. Now let's talk about the most likely scenario.
Most likely scenario.
The most likely scenario is that the Red Queen isn't going away anytime soon. And if you're familiar with the Red Queen, it's the sense that even if you keep running, you're sort of running in place, just like the Red Queen in Alice in Wonderland, because you're always up against this other entity, meaning viruses, that are constantly evolving and adapting, as you are also constantly evolving and adapting. So even if we totally solve protein folding, we can model the 3D structure of any protein, any sort of virus, even then, I think we're still going to have to face new diseases, new types of viruses that will come into the world, and maybe they're immune to some of our techniques. I don't think we can declare victory yet on viruses always adapting and evolving. Many scientists have been sounding the alarm on the potential of a superbug because we've been using antibiotics very often, and perhaps more often than we should, which leads to antibiotic-resistant viruses. And so I think in order for us to combat the potential worst-case scenarios, we need to keep progressing. And AlphaFold is one of the ways that we can keep progressing. It's also, when I think about the most likely scenario, it feels like we're moving from this paradigm of depending on chance encounters and chance discoveries from lone scientific individuals who are just really curious to a more systematic approach to taking care of viruses and diseases. So I think it's worth talking a little bit about how we discovered penicillin and how that's different from how we'll discover diseases in the future. So the discovery of penicillin was made by Dr. Fleming in England, and he was analyzing the bacteria to find a way to create the world's first antibiotic. And it just so happened that a little bit of penicillin mold flew into his lab through the window and landed in his petri dish. And he noticed that this little penicillin mold was actually preventing the growth of the bacteria. And that's how we discovered the first antibiotic that absolutely changed the course of history. It improved life expectancy. Many historians believe that's why the Allies won World War II, because we could essentially take wounded soldiers, fix them, and put them back on the battlefield, whereas the Axis, most people who got an injury, they couldn't fight anymore because they didn't have antibiotics. So it is tremendous, the impact of something like penicillin, and that was really a chance discovery. There wasn't a systematic approach. Now, with AlphaFold and similar techniques, we no longer have to do guesswork and have to depend on something floating in through the window. We can actually have a systematic way for discovering what a virus looks like on the structural level and then coming up with treatments based on our knowledge. In closing, I'd just like to say that I am so optimistic about the future. Last episode, we talked about the Great Acceleration and all of the discoveries that are being made, all of the new paradigms that are shifting. And this is just yet another example. So if you're curious or passionate about solving these types of problems, I would definitely encourage you to think about what potential applications could derive from this AlphaFold breakthrough. And the more we have knowledge of how biology works, how systems work, how AI works, we can really create a better and better future. So I've never been more optimistic about the future. And thank you for listening. I wish you the best, and I'll see you next time.
The past, the present, and the future.
Our computer is picking up a strange signal.
The past, the present, and the future, baby.
If you enjoy thinking about the future as much as we do, we invite you to join the HTF community. Simply go to hencethefuture.com, scroll to the bottom of the homepage, and add your email address next to the button that says Enter the Void. You can also follow us on Instagram and Twitter at hencethefuture. And, most importantly, we encourage you to please rate and review the show in Apple Podcasts if you haven't done so already. Our team reads and appreciates every single review. Thank you again for listening to today's episode and for staying curious, and we'll see you next week.